Okay, I'm going to talk about the general problem of artistic universals, and just a little bit of history. How did I get into all this? It's not what I normally do for a living. I do cognitive neuroscience and behavioral neurology, as Eric pointed out. What I usually, what happened on this particular occasion is about 10 years ago, I was walking through the temples in India and looking at some works of Indian art. You should see some examples. So my talk is Science of Art. Are there artistic universals? How does the brain respond to art? And I started looking at these sculptures from the 11th century and earlier. That is the goddess Parvati, who's supposed to be the epitome of feminine grace, sexuality, sensuality, poise, dignity, charm, everything you associate with being a woman. So I started, initially my reaction was this is all religious iconography. I had a very Eurocentric view of Indian art. I said it's pretty, but it's not really great art, you know. But all that changed during that visit. I was walking around and something happened, and they started haunting me night and day, and I started seeing them as works of art as opposed to archaeology or ethnology or religious iconography. Then I started wondering, why are these works of art so effective? What's going on in the brain? Obviously, it's happening in the brain. What's going on? So I started looking at the history of ideas about art, especially the British historians who came to India, the Victorians, and also well into the 19th century, looked at these things and they said they're hideous. Because, for example, that doesn't look like a real woman. The breasts are too big, the waist is narrow, the hip is broad, and it doesn't look like a real woman. And of course, in saying this, they're missing the whole point of art, which, as you all know, it's common knowledge these days, is not about realism. I mean, I can take a $5 camera, take a snapshot of Semir Zeki, you wouldn't pay me a dime for it, okay? However realistic it might be. So it's nothing to do with realism. On the contrary, it's about deliberate hyperbole, exaggeration, distortion even, okay? But you can't randomly distort an image and call it art, although where I come from in La Jolla, they do that. It has to be systematic or lawful. So the question then becomes, what are the laws? How can you distort it and still call it art? And that got me thinking about what I whimsically, that's another example, call the laws of art. And I initially came up with about 8 or 9, and maybe now I come up with 10 or 11. It doesn't matter, 8, 9, 10. The point is there are a finite set of laws, and these are rules of thumbs or heuristics that artists either unconsciously or consciously deploy to more optimally titillate the visual centers in your brain. I'm going to only talk about visual art, more optimally excite these areas than you could with natural images. And by the way, I want to make a distinction between art and aesthetics, which is the thing overlooked by that critic, Hyman, okay? So art and aesthetics, and all of my laws pertain to aesthetics, and that too is true of Semir's work and of Marge Livingston, but undoubtedly aesthetics is an important part of art. But the reason I make that distinction is I can throw a toothbrush here, and I say, I call it art, therefore it is. And I can't discover anything lawful about that, so I stay away from that. So we're really talking about aesthetics rather than art, okay? So what are these laws of art? But before I get into them, I want to tell you that what I've tried to do with each of the laws, if possible, and I succeed in some cases and not in other cases, is there are 3 parts of a triangle, 3 corners of a triangle: what, why, and how. What is simply a simple statement of the functional logic of grouping, peak shift, or isolation, or any one of the number of laws which I'm going to talk about. Okay, that's what psychologists do. Then there is why, which means the evolutionary rationale for that law. Why does it exist? Why did it evolve? Why does it have that logical structure? Maybe there is no reason. It's a so-called spandrel. But you have to look for a possible rationale for that law. Now, by the way, I was saying that I want to make it clear to all of you here that I'm a strong believer in evolution through natural selection. I don't believe in intelligent design. Okay? And it's a bit ironic that our president is pushing this idea of intelligent design when his own existence is a living negation of any such principle. Okay? As you can see from that slide. Okay. Okay, let me illustrate. Okay, by the way, going back to this. So what, why, and how, of course, is the neural instantiation, which is something that Marge and Semir have pioneered. And we need to know that too, because you need to know what the nitty-gritty neurology is. But what I'm claiming is without all 3 in place, you're in the dark. For any biological phenomena, whether you're talking about laughter, sex, you name it, crying, you need all three in place. And many previous approaches to art have failed because they tend to focus exclusively on one or the other. For example, the evolutionary psych approach is, by the way, it's like saying, why do I like to go to aquarium? Many people like going to the aquarium. Why is that? Well, it's because in Devonian times, we were swimming around with fish in the sea, and some residue of this is still there in your brain, hence you like looking at fish. Now, this illustrates the absurdity of just looking at it from one point of view, okay? Now, I'm going to try to therefore cover all 3 points of view. Let's take a simple example, grouping. I'm sorry about the colors there. I need Marge's help here. But anyway, these are supposed to be yellow, these three. And the brain instantly groups those and segregates them from the background. This is called grouping, right? Now, the question is, what, why, and where? The principle is easy. It's grouping similar features, like similar colors, similar directions of movement, similar depth, even in remote regions of the visual field, are automatically linked by the brain and segregated, okay? Now, why does that happen? I'll tell you. Another example from design, fashion design. If I wear a tie, which I'm not wearing now, say a loud tie with red splotches or bluish splotches, then it's good to wear a jacket with some blue in it. So they'll say, well, the blue picks up the jacket, the color of the jacket. Now, is this just marketing or hype, or is it telling you something about the brain? I claim it's the latter. It's telling you something about the brain. Namely, vision evolved. One of the main reasons vision evolved is for segmentation of the visual scene. And one of the ways in which you achieve segmentation and detection of objects is grouping. Because very often an object has to have the same color throughout. So for example, you're looking at a lion through fluttering green foliage, a yellow lion. And all you see is lion fragments. But the brain instantly glues those fragments together, groups them together, and says, wow, that's a lion, let me get out of here. Okay? Now, what I'm claiming is in addition to the grouping, there's a jolt sent through the limbic system saying, my God, that's a lion. You know, eyes swivel towards you, orient, and then you run away or grab your gun and shoot it. Okay? So what I'd like to claim is, so that's the what, and we've talked about the why. It's to defeat camouflage, what and the why. We don't know the mechanisms yet. Tony Morgan is working on it. One is synchronization of spikes, okay? But probably that's wrong, okay? But another is cooperative interactions between neurons which are tuned to the same property. But these are difficult ideas to test, but people are testing them, and we'll get to it sooner or later. Okay, so now, by the way, I want to make one other additional point here. The old MIT model of vision, mainly perpetuated by Meier and his disciples like Whitman Richards, is that you start with the lion fragments, you group, then you segment, then you recognize and say, aha, limbic activation, run away, okay? But I'm saying this is all bogus. This is approximately true, but in reality, at every stage in processing, what happens is there's a partial solution to the object, and then you send it back to the previous area. So you do a sort of 20 questions game with the visual image until finally the image crystallizes and you say, aha, it's a leopard, let me get out of here, okay? Or it's a mate, let me pursue it. So what I'm saying is what the artist is doing, visual artist, is trying to manipulate his image to create as many little ahas as possible. And what I'm claiming is there are, in fact, connections to the limbic system at each stage of processing. So it's a multiple mini ahas theory of art, okay? So in other words, it's like art, in other words, is like visual foreplay before the final climax of object recognition, okay? And that's what the artist is doing, okay? Now I go on to other laws. The second law is peak shift or hyperbole. And what do I mean by that? Well, in the operant literature, it's well known that if you, I'm going to find the button here, okay. If you train a rat to discriminate a square from a rectangle, give it cheese every time it sees a rectangle, very soon it goes to the rectangle. Now what you do is, after it has learned, you give it a long, skinny rectangle. And the amazing thing is the rat prefers this to the original rectangle. You say, well, that's kind of stupid. Why is it preferring this long, skinny thing to the original? Well, it's not stupid because the rat has learned a rule, namely rectangularity. Not that particular rectangle, but the aspect ratio. So the more rectangular, the better. And he says, wow, what a rectangle. And it goes to that. Okay? This, by the way, is the same principle underlying caricature. What happens is you want a caricature of Nixon's face. You take his features, subtract it from the average male face, and take the difference and exaggerate it. And you say, wow, that looks more like Nixon than Nixon himself. Okay? And that's what's going on here in caricature. And indeed in high art, if you look at the Chola bronze I showed you earlier, you take the normal female and then you subtract the normal male from the normal female, you're going to get breasts and hips and that swaying posture, and then you amplify the differences. But that's not enough. You're just going to get a sexy woman if you do that. How do you give grace and elegance and poise and all of that? There you go into a more abstract space, which I call a postural space, which is to do with the angle of the shaft and neck of the femur and the lumbar lordosis. So certain postures I can't do, even if I try, but a woman can do it effortlessly. So you go in there, do the subtraction, and amplify it. You don't say, yuck, it's an abnormal woman, like the Englishman did when he looked at it. You say, wow, what a goddess, okay? Now, you say that's all fine about, response to caricatures, response to peak shifts in women and men, for that matter. But what about more abstract art? What about Henry Moore? Okay, what about Rodin? Okay, I'll answer that. Okay, so you need to look at ethology, look at Tinbergen's work on gulls. So that's a seagull, mother seagull with a long yellow beak with a red spot. And the chick, as soon as it hatches, starts pecking at that red spot, begging for food. The mother regurgitates half-digested food into the chick's gaping mouth. Chick eats it and is happy. Question is, how does the chick know who is an adult seagull mother? Okay, the answer is, Tinbergen found you don't need a mother. You pluck the beak away, wave it in front of the chick then pecks at the little red spot. Well, you say, that's kind of stupid. Why is it pecking at that thing? It's not even a mother. Well, it's not stupid. Again, vision is about doing as little computation as possible to get the job done. Do shortcuts, in other words. And it knows in nature the only time it'll see that thing with a yellow spot, with a red spot, is when there's a mother attached to it. Okay? You never see a mutant pig with a beak or a malicious ethologist waving a beak. Okay? So the chick's brain can take advantage of that in its hyperstriatum or tectum and wire it in. Okay? Now, Tinbergen then found you don't even need a beak. You can take a long stick with a red spot, and the chick still pecks at this, showing there's some tolerance in the receptor field. It doesn't care exactly if it's identical, right? But even better, and this is the climax, he took a long stick with 3 red stripes. The chick goes berserk. And all of these chicks are mesmerized, ignoring the real beak and mother, and going to this fetishized beak, and they start fetishizing it. Why? What I maintain is, these cells have we don't know what the alphabet of human visual perception is for recognition of form. And what's happening is, the chick during millions of years of evolution has developed a stimulus which more optimally stimulates those neurons than a real beak. This has to do with the way in which the receptor field is wired up. Maybe there's more red contour, red line or something, so it fires more and sends a bigger jolt to the limbic system, saying, wow, what a sexy beak. Okay? And the chick goes crazy and starts pecking at this, even though, and this is critical, even though it does not resemble a real beak. Okay? So that brings me to my punchline about art, and that is, if the seagulls had an art gallery, they would hang this long stick with the red stripes on the wall. They would pay millions of dollars for it. They would call it a Picasso. They would worship it, but without understanding why, because the damn thing doesn't look like anything. And this is what all of you in New York are doing when you buy works of contemporary art. Okay? Okay. An example, and God knows what neurons are being titillated. Now, the next principle I want to tell you, by the way, I have a list of 9, and I can only tell you about 3 given the time limitations. The next principle is the principle of isolation, and that is alluded to briefly by Marge. The question is, somebody like Picasso can make a little doodle of a nude or a bull, and that's much more evocative and powerful than a full-color National Geographic picture of a bull or a 3D or a pin-up in a Playboy, okay, or a Chippendale calendar for that matter. Okay, so why is that so much more, a little doodle by Klimt or Picasso, much more effective than a full-color picture with shading, with color, with more information? All right, so here is the paradox. Less is more, the art of understatement. So am I not contradicting myself? Earlier I said hyperbole, now I'm saying understatement, okay? But through such contradiction, you can discover new principles by resolving paradoxes. In this case, I think the resolution is, even though you've got 100 billion neurons in your brain and more than 30 visual areas, as Samir has shown so elegantly, in spite of that, there's a bottleneck of attention. You can only pay attention to a limited set of limited parameter at a time. Therefore, what the artist has done, if you see a full-color nude or a full-color bull, there's all this irrelevant information. A nude of me or Samir or anybody else has this color, hair, and all of that. Now, the critical information for a nude, or for a bull for that matter, comes from the outline. Now, when you look at a full-color natural image, the brain has to ignore all that irrelevant clutter and pay attention only to the outline, given its limited attentional resources. So what the artist has done is cleverly removed all that irrelevant clutter, presented only the outline, and exaggerated to produce peak shifts. And that's why that image is effective. Well, Ramachandran, what is the evidence for this? Okay, comes from neurology, comes from looking at patients with frontotemporal dementia, Steve Miller, but also in the old days from autism. Here I want to show you a drawing by a normal 8-year-old child of a man on a horse. It looks hideous, right? Like a two-dimensional cutout. Here, by the way, is a drawing by a 6-year-old autistic child who can barely tie her shoelace and certainly incapable of language. And look at her horse. It is jumping out at you from the canvas. It's animated. It has so much movement and energy. And then look at Leonardo da Vinci's horse. If I hadn't told you that, and if we're not an audience of artists, if I do a poll, more people pick this than that as being more artistic, saying, well, there are too many lines here. Like that guy said, too many notes in Mozart's composition, okay? So here's the paradox. Here is this 6-year-old autistic child producing a more beautiful drawing than Leonardo da Vinci. How is that possible? Well, I think it's because of attention. It's because many other modules in the autistic child are not functioning, so the child is able to more spontaneously allocate all its available attentional resources to the one functioning module, which in that case, in Nadia's case, may be a right parietal, which we know is involved in the sense of artistic proportion. So this spontaneous reallocation of attentional resources makes her better at judging sense of proportion and creating this beautiful horse. Okay, now, I'm going to do a digression. This has nothing to do with art. It's about autism. In the last 5, 6 years, we've been working on autism, and it is relevant to art, as you'll soon see. What is autism? As you all know, it's a complete social isolation, social withdrawal, poverty of language, linguistic communication, especially pragmatic aspects of language, lack of empathy, both emotional empathy and cognitive empathy, inability to place yourself in somebody else's shoes, look at something from somebody else's point of view, theory of other minds, failure of imitation, and difficulty with metaphor. So I was listening to this and I said, my God, it's a fascinating cluster of symptoms seemingly unrelated to each other. Then I was listening to a talk. This is about 1999 at Cogneuro. I was listening to a talk by Vittorio Galazzi and Giacomo Rizzolatti, and they were talking about mirror neurons, and you already heard about this. Mirror neurons in the frontal part of the brain and also to some extent in the parietal, which will fire when a monkey reaches out and grabs something, grabs a peanut, puts a peanut in its mouth, pulls a lever, pushes something, different neurons for different tasks. This has been known since the time of Vernon Mountcastle. They're just motor command neurons, okay? But what Giacomo Rizzolatti and Galazzi found was some of these neurons will also fire when the monkey watches another monkey doing it. It's as though the monkey were putting itself in the other monkey's shoes and has a theory of the other monkey's mind, so to speak. So I looked at this and I said, my God, the list of properties which you see of mirror neurons is identical to the deficits of autism, okay? Look at that slide. It shows you the similarities, striking similarities between the deficits. This is, by the way, in 2000, and I showed this at the Society for Neuroscience. And we said, well, first of all, we have to prove this is true. It's a theory, compelling. How do you prove it? We found an autistic child. There's a technique called EEG, and you can measure a waveform called mu wave in the center of the scalp. And this mu wave, which it turns out gets suppressed when the animal performs an action. Sorry, not the animal, the person performs an action, like reaching out and grabbing something. Okay? So mu wave suppression indicates some skilled movement, semi-skilled movement. But the amazing thing is, it also gets suppressed when the child or the person looks at somebody performing the same action. So we said here we have a technique for monitoring mirror neuron activity, perhaps in a normal human being. We then got a number of normal people, and sure enough, that's what happens. So we suggested, and we're the first to suggest, that mu wave suppression is a correlate of mirror neuron activity. And there's another group reporting with fMR that you can do similar experiments. But then we did the critical experiment. We brought in an autistic child. And the autistic child, we recorded mu wave. And when the child performed an action, the mu wave suppression occurred. But when the child watched somebody else, there was no suppression. So we presented that at the Society of Neuroscience, 2000, along with this theory, and nobody believed it. There's a whole autism mafia, it turns out, who has their own pet ideas. The standard ideas about autism is one, that they have a defective theory of other minds. Comes from Jutta Frith and from Simon Baron-Cohen. Well, what the hell does that mean? They have a defective theory of other minds. That's just a statement of the observation. Of course they have a defective theory of other minds. That's the definition of autism. So it's not taking you very far, right? Even though I respect them, by the way. But this particular theory doesn't take them very far. The other notion is anatomical changes. You find changes in the cerebellum. Again, it doesn't tell you very much because as Eric here knows, if you damage the cerebellum in an adult or in a child, you get intention tremor, you get ataxia, you get nystagmus. You don't see any of that in these children, right? On the other hand, with mirror neuron deficit, you get precisely those deficits which are unique to autism and not seen in other disorders, by and large. So we said, yes, we have found this, but N of 1, I'm not going to tell you the pig joke again, but I will say all the great discoveries in neurology, Broca's aphasia, Wernicke's aphasia, callosal syndrome, split brain, blind sight were discovered in an N of 1. So I'm a big fan of N of 1. Okay, now, that's showing you mu wave suppression. Mu wave suppression is my token graph for the meeting, okay? And then, so in conclusion, we believe we may have found, May was added, I added May, that's a slide from my graduate student, Lindsay Obermann, who spearheaded a lot of this work. And now there are many groups who are claiming that there's a mirror neuron deficit in autism. So we think we're on the right track. The other thing I wanted to say briefly, do you have 2 minutes? Or? Okay. Other thing I wanted to say briefly is, I'm not going to go over all of these, but I will talk about metaphor, the ability to link seemingly unrelated concepts in your mind. Now, it turns out autistic children are bad at that. Why would they be bad at that? Well, we came across this stimulus. These are Martian alphabets, which we drew. Like A is A, B is B. One of these is Kiki, the other is Booba. How many of you think that's Kiki, that's Booba? Raise your hands. There's one mutant there, but almost all of you, even though you've never seen it, that's Booba, that's Kiki. And we've got a number of such stimulus pairs. This is an example of a visual metaphor of cross-modal integration. Kiki for that because the sudden inflection of the visual contour mimics the ki sound in the auditory cortex and the ki of the tongue hitting the palate in the drawing. Now, where does that happen? We now have evidence it's in the inferior parietal lobule, especially in the left hemisphere. We've got about half a dozen patients with damage to the left inferior parietal lobule, mainly Gerstmann syndrome. Some of them have components of apraxia. Fluent in conversation, otherwise normal. Give them this, they're a chance level. And that makes sense because that's where all the different sensory inputs become confluent. Not only that, both these patients and autistic, and by the way, in autistic children, they're at chance level. 5 out of 6 patients with autism, high-functioning autists, don't do the Booba-Kiki tasks. And again, bear in mind that this is a mirror neuron type task. Because what's going on here? You're establishing a congruence between one map, auditory map, and another map, a visual map. Just as in mirror neurons, you're establishing a congruent between movement and motor maps and on the one hand, and visual maps on the other hand. So this also is tapping into mirror neurons, and it's compromised in autism. So we think we're on to something here. And lastly, I'm concluding with this, both autistic children and people with left angular gyrus, inferior parietal lobule damage, are terrible with metaphor. We call this metaphor blindness. If you give them a metaphor, all that glitters is not gold. What does that mean? Remember, here's a person who's perfectly fluent in conversation in other respects. There's a mild anomia, but other than that, they're fine. They have some left-right confusion. All that glitters is not gold. The patient says, oh, well, that means if you have a shiny metal, it doesn't mean it's gold. It could be copper. It could be an alloy of some kind. I said, I know, but is there some deeper meaning than that? He said, oh, yeah, the deeper meaning is you shouldn't go to jewelry shops because they'll sort of rip you off by giving you. You have to take the specific gravity and then you'll know. That again shows he's not stupid. He's telling you to take the specific gravity. So in other words, these people are not stupid. They clearly comprehend what you say at a literal level. They're not stupid, we know that, because they often give you long-winded, elaborate, even ingenious interpretations of the proverb, but completely missing the point. Just like the people who review my papers. Okay. Anyway, I'm concluding. I'm done with that. Thank you.